Alright, so in the last video we learned how to recognize the parametric form of an ellipse. It looks a lot like the parametric form of a circle that we had seen in the previous section, but for a circle the coefficient on the cosine and sine terms always are the same number, and that number represents the radius. However, with an ellipse, those numbers are going to be different numbers. And what they represent, loosely speaking, is how far from the center in the x and y directions respectively the ellipse can travel. They bound your ellipse if you want to think about it that way. What I want to do in this video is kind of expand on that. Now that we know that this parametric form represents an ellipse, maybe we need to study a little bit more about ellipses to sort of unpack all the information in that equation. So first of all, when you think about an ellipse, you might just think of like an oval, like a circle that you smush down, loosely speaking. But it's a little bit more interesting than that. If you think about a circle that is all the points that are a given distance away from the center, then you can come up with the definition of an ellipse pretty similarly. And that might seem counterintuitive because when you look at an ellipse, you're like, no, this point right here is a different distance from the center than this point is right here, for example. And that's true. With an ellipse, it's not that all the points on the outside are the same distance from the center. It's that the sum of the distances to the foci of the ellipse, foci is the plural of focus, the sum of the distances to those two foci are always a constant. So what I'm saying is, if I think about some arbitrary point out here on the outside of this ellipse, and I measure how far it is from this point down to this point here, which represents one of the foci, and then I measure how far it is down to this point over here, which represents the other foci, and then I add up those two lengths. That sum of the distances is what's always constant for any point. Kind of imagine that you had like a thumbtack here and a thumbtack here, and this is a piece of string. You kind of stretch this string taut as you draw all the way around the outside of the ellipse to trace out this shape. And that's because the sum of the distances to these 2 points is always constant in an ellipse. So that defines the two foci of an ellipse, but those aren't the only vocabulary words we need to understand. The next two vocabulary words that I want to talk about are the major and the minor axis. The idea there is, we can't really use the term diameter for an ellipse, but that idea of how far it is from one side of the ellipse to the other side is really important. The challenge is that answer differs. If I measure the distance across the ellipse right here on my horizontal axis, I'm going to get a different distance than if I measure the distance across my ellipse, I don't know, over here maybe, right? Maybe you can kind of see that the red line is longer than the blue line. In fact, the red line is the longest distance it'll ever take to get from one side of the ellipse to the other. And this line that I'm drawing in green represents the shortest distance it could ever take to get from one side of the ellipse to the other. Those feel like important things, and they are. They're the major and minor axes respectively. So the minor axis is what's pictured in green here, and it's just the shortest distance to get from one side of the ellipse to the other. And the major axis is what's pictured in red here, and it's the longest distance to get from one side of the ellipse to the other. The foci are the 2 points that sort of define the ellipse, more on that later. And that leaves two more vocabulary words. The center, which is just, well, the center, nothing too interesting there. And the vertices. The vertices of an ellipse are the 4 points where the major and minor axes intersect with the ellipse itself. So what I'm saying is when I drew this line in green intersects with my ellipse in blue up here at this point and down here at this point. That means these 2 points are both vertices of this ellipse. Similarly, the line in red intersects my ellipse over here and also over here. So those are 2 more vertices of my ellipse. An ellipse will always have 4 vertices, and they'll always fall at the intersections of the major and minor axes and the ellipse itself. A comment that I want to make. In our class, the major and minor axes will always travel vertically and horizontally. You could define an ellipse to kind of be tilted, loosely speaking, but we won't get into that in our class. So in our class, the major axis will always be a horizontal line segment or a vertical line segment. That distinction is rather important. Over here, the major axis is on the horizontal. Over here, the major axis is on the vertical. The reason it matters whether your major axis is horizontal or vertical is because it turns out the foci always lie along the major axis. So in this picture, we see the foci right here at negative C and positive C, 0 respectively, along the major axis. But in this picture, where our major axis travels vertically, the 2 foci no longer have a y-coordinate of 0, but instead have an x-coordinate of 0, as they lie up here at 0c and down here at 0, negative c. The standard is to use the letter A to represent half the length of the major axis and the letter B to represent half the length of the minor axis. And with that naming convention, when the center is at 0, 0, if the major axis is horizontal, we'll always have vertices at A0 and negative A0, and also at 0B and 0, negative. However, if your major axis falls along a vertical line, then everything just kind of switches. Instead of A representing the X coordinate, A represents the Y coordinate because A is half the length of the major axis. So again, if we're centered at 0, 0, we'd have a vertex at 0, A and 0, negative A, as well as B, 0 and negative B, 0. One more thing I want to show you as far as vocabulary goes for an ellipse, and it deals with the foci, which I talked about briefly already. The foci always fall along the major axis. So if your major axis is horizontal, we can kind of picture them somewhere over here to the right of the center and to the left of the center. And if your major axis is vertical, we can picture them up here and down here above and below the center respectively. Suppose you want to know exactly where they were though. To locate these two different foci, I think it'll help to have a more concrete example. So what I want to do is I want to go back and revisit an example that we looked at previously. We have this ellipse pictured in green here, and our major axis goes along the horizontal and our minor axis goes along the vertical. So we know that the foci must be somewhere here along the major axis, somewhere to the right and the left of the center. But where exactly do these red dots show up? Well, the way we can locate them is we can take advantage of the fact that if I pick any point on the outside of the ellipse, the sum of the distances from that point to my two foci must be a constant. So I can pick any points I want on the outside of this ellipse, but maybe if I'm kind of clever and pick a point right here and then another point up here, it'll minimize the work that I need to do for my calculations. So let's first figure out how far it is from these two red foci to this purple point right here. That's going to be a bit of a challenge because we don't know the coordinates for these red points. So maybe what I'll do is I'll say that the x coordinate of this point is 2 plus some number c that I need to figure out, and the y coordinate of this point appears to be negative 1. And for this point, I could say that the x coordinate is 2 minus that number c that I need to figure out, and the y coordinate is negative 1. By naming the x coordinates this way, really what I'm doing is I'm saying the distance from the center along this major axis to either of my two foci is exactly c, which corresponds with the letters in the naming convention that we saw down here. Now that I've put that variable in there, all I have to do is solve for c. Let's first calculate how far it is from these two different points to this point in purple. I know that this point in purple has an x coordinate of 5 and a y coordinate of negative 1. So the distance from this point to this point is just the difference in their x coordinates, which is 5 minus 2 plus c. Maybe I'll call that d1 for distance 1. And if I instead wanted to figure out how far this point is from this foci way over here, a distance that maybe I'll call d2, what I would have to do is take that same 5, the x coordinate of this point, and subtract 2 minus c, the x coordinate of this point. I can simplify each of these expressions a little bit. 5 minus 2 is 3, so I would have 3 minus c up here. And then down here, if I take the negative and distribute it through, I got negative 2 plus c. 5 minus 2 is 3 again, but now I would have 3 plus c. Really what I'm interested in is the sum of these two distances. d1 plus d2 would just be 3 minus c plus 3 plus c. In other words, 6. The c's cancel out, which is really nice. What that means is, if I could come up with an expression that represented the distance from this point in red to this point up top, and another expression that represented the distance from this point in red to this point up top, I would know that the sum of those two distances would have to be equal to 6, because the distance to any point on the outside of the ellipse has to be the exact same, and I just calculated that the distance to this point out here is exactly 6. Another comment that I can make: thanks to the symmetry of an ellipse, this foci will be as far to the right of the center as this point is to the left of the center. So the distance from here to here is the same as the distance from here to here, and clearly the distance from here up here is the same. What I'm saying is I have the same triangles on either side, which means that this hypotenuse must be the same as this hypotenuse. If I call the distance from this foci to the top here, I don't know, maybe e or something, just because I'm running out of letters. Taking advantage of the fact that this length is the same as this length, 2 times e must be equal to 6. Therefore, e must be equal to 3. It's hard to see, but I think what I now have are two sides of a right triangle, so really I have all three sides of a right triangle. I know that E is 3. I know that the length of this side of the triangle is 2, because the length of the minor axis is 4. So the distance from the center up to this vertex must be 2. So since C represents the distance from this point out to this foci, I can use Pythagorean theorem and say that a squared plus b squared equals c squared. In other words, 2 squared plus c squared equals e squared, or 3 squared. I got 4 plus c squared equals 9. I got that c squared is 5, and therefore c is the square root of 5. If I really wanted to locate these two foci, I could now do it. Remember, the coordinates of this focus were at 2 plus c comma negative 1, but now that I know that c is root 5, I can say that the coordinates of this focus is 2 plus root 5 comma negative 1, and the coordinates of this one over here are 2 minus the square root of 5 comma negative 1. And you're like, okay, cool, you can do a whole lot of work to locate the foci. I'm not sure that I ever want to recreate that. Well, good news. We can do that again, but do it a little bit more generically, and that'll end up providing us with a really nice equation to figure out the coordinates of these foci. If instead of looking at an ellipse that's centered over here at 2, negative 1, I consider this ellipse that's centered at 0, 0. I'm again going to let C represent the distance along the major axis from the center to the foci, and let A represent the distance from the center to the vertices along the major axis, and B represent the distance from the center to the vertices along the minor axis. Then I can take advantage of the fact that the distances to two perpendicular vertices must be the same. So in this picture, the distance from here to here must be the same as the distance from here to here. And since I've already drawn all over this picture, maybe I'll instead do the argument with this picture. Let's first consider the sum of the distances from the two foci to this point 0a, pictured up here. Well, just by looking at the picture, I can figure out the distance from this vertex at 0a to this closer foci at 0c. Since a represents the distance from here to the center, and c represents the distance from here to the center, the distance between the two would just be a minus c. And I can use a similar argument to figure out how far it is from this vertex all the way down here to this focus. The distance from the center up to the top is A. The distance from the center down to this focus is C. So the total distance is A plus C. I want the sum of those two distances, so I want A minus C plus A plus C. And when I simplify this expression, the C's cancel out, and I get 2A as my answer. The sum of the distances from the two foci to the point 0A is 2A. Anytime A represents the distance from the center to the vertex that is along the major axis, and C represents the distance from the center along the major axis to either of the foci. I can now consider the sum of the distances from the two foci to the point B0, pictured as this diagonal line in green right here, and this diagonal line in green right here. Let's first worry about the diagonal line up top. It's a little hard to see with all my chicken scratch in here, but maybe you can see a right triangle where the vertices of that right triangle are the vertex at B0 that I'm interested in, the focus at 0C that I'm interested in, and the center of the ellipse at 0, 0. The length of this leg, the distance from the center to this focus, is just C. The length of this leg, the distance from the center to this vertex, is just B. I don't know the length of the diagonal, but I can use Pythagorean theorem to figure it out because this is a right triangle. This squared plus this squared must be equal to this squared, so this must be equal to the square root of B squared plus C squared. That's the distance from one foci to this vertex, but really what I need is the sum of the distances from each of the foci to this vertex. So I don't just need this distance, I need to add to that this distance pictured right here. Good news though, because of the symmetry of an ellipse, the distance that we just figured out is the exact same as this distance here. So the sum of the distances from the two foci to this point B0 is just the square root of B squared plus C squared plus the square root of B squared plus C squared. In other words, 2 times the square root of B squared plus C squared. I know your patience is probably running out, but look what we just figured out. This vertex and this vertex are both along the ellipse. The sum of the distances from the foci to any points, vertices or not, on the ellipse must be the same. Therefore, 2a must be the same as 2 times the square root of b squared plus c squared. If I divide both sides of this equation by 2, I get that a must be equal to the square root of b squared plus c squared. And if I square both sides of the equation, I get a squared equals b squared plus c squared. Remember, our goal was to try to locate the foci. We're assuming that we know a and b and we want to figure out c. So I can solve this equation for c if I subtract b squared from both sides to get that c squared is equal to a squared minus b squared, a really cool equation that gives you a ton of information about the ellipse. It relates together the distance along the major axis that the foci lie from the center with the distance along the major and minor axes that 2 of the vertices lie from the center, which is kind of cool. However, I wrote that it's bonus here because I don't think I ever asked you to do any calculations, but I wanted to show you how you could come up with the foci if you really needed to. You take this formula right here and apply it to this example. The distance along the major axis to the vertices, 3 right here, is my value of a. The distance along the minor axis to my vertices is this 2 right here, which represents the letter b. If I wanted to know c, the distance from the center along the major axis to the focus, all I would have to do is say that c squared is always equal to a squared minus b squared, that cool little formula that we just came up with down here. And since I now have values for a and b, 3 and 2 respectively, I could figure out c pretty easily. 3 squared minus 2 squared is 9 minus 4, which is 5. So c squared is 5, which tells me that c is the square root of 5. And with that information and the knowledge that the foci always lie along the major axis, I could figure out that this point is at 2, the x-coordinate of the center, plus that root 5. And this point has an x-coordinate at 2 minus the square root of 5. I think that's all kind of cool. Anyways, the purpose of this video, really what I was trying to get at, is to teach you some vocabulary about an ellipse and to kind of come up with some connections between those different vocabulary words. If you leave this video with knowledge of the major axis, minor axis, the foci, the center, the vertices, and you understand how the foci and the vertices that are along the major and minor axis are related together with this formula, you've definitely picked up everything that I'd ever want you to know about the vocabulary of an ellipse.